Practical demonstration of Martian resource harvesting and transformation. We hear a lot about ISRU, and I'll have comments on that in a minute, in situ resource utilization. And I've thought a lot about what it is we're actually doing when we talk about that. You heard in the first talk an overview of the case for Mars, the Mars Direct variations, which probably, from NASA's point of view, they'll point to the DRA, the Design Reference Architecture 5.0, as the current plan for going to Mars. And to summarize all the stuff going on in here, you put everything down on the surface first. You have 26 months from the time you launch all the stuff to the time you launch the people. And in that 26 months, you put down the habitat, you put down the ascent vehicle, you put down the power system, and ideally, the ascent vehicle is all loaded up with propellant ready to go. It turns out that's one of the biggest things you have to take with you. 27 tons of oxygen, that's a few hundred tons in low Earth orbit, which is, even with the 100-ton launch vehicle, that's still multiple launches. It's a big deal to have to get that to Mars. If you can make that on Mars while you're waiting around for a year and a half for the human crew to launch, you just saved yourself a lot of complexity and money and time. And I like to think have moved forward the day we're going to do this by a decade. If we can demonstrate we can make oxygen on Mars. Now, the issue of making the fuel, well, it turns out the fuel is only, the 7 tons. So it's best to think about the 27 tons you might save first. There's been a lot of public interest in this, and someone mentioned the Martian earlier. See if I can do this. This is Jim Green at headquarters.
That under certain
What he's saying, under certain circumstances, liquid water can be found on Mars. And this is from the website of the Martian. And what Matt Damon is saying there is surprise. Sorry, I didn't think about hooking up the sign. That would have been a nice thing a nice thing to do. But the linking of what you've been hearing about, just heard about from the previous speakers, from Adrian Brown, and what's going on with planning for human exploration of Mars, the point I want to make, and that website in the front page of the Martian movie makes so well, is that these things are coming together. These things are converging. What we know about Mars from scientific research, what we are dreaming about Mars for sending people is becoming real, is becoming, humans to Mars in a decade, and most notably, the organizations within NASA responsible for doing robotic exploration and doing human exploration are actually amazingly starting to work together. The 2020 mission is evidence of that. The Science Mission Directorate, the Human Exploration Directorate, and the Space Technology Directorate are all starting to work together. I'm not saying they're singing Kumbaya yet, but things are coming together. So, okay. Just a few tips, my personal thoughts, my personal imprint on so-called in situ resource utilization, ISRU, which I think you've all heard about, in situ, stuff you find there living off the land. So first of all, utilization is kind of a mundane thing. When we aerobrake, when we're using in situ resources, big deal. When we use a parachute, we're using in situ resources. My favorite examples are when you do a gravity assist, or even better, when you do in-space manufacturing, you're taking advantage of vacuum. Vacuum on Earth is a scarce resource. So, nothingness, the lack of gravity in microgravity, the lack of air in vacuum, those are resources we're utilizing. It gets exciting when you actually start transforming those resources into something else. And so mostly when people talk about ISRU, they're talking about going out and harvesting resources and turning them into something else. And that's really what we're focusing on here. So in our case, making oxygen from carbon dioxide. If you make hydrogen from ice to make fuel, or make methane from ice, then you're doing resource transformation, and I believe that's what's transformational. I notice here I'm mixing two kind of interesting metaphors. The first thing you want to worry about is the low-hanging fruit, the easy stuff to do, and that low-hanging fruit, I'm going on to say act like a tree with low-hanging fruit, I guess. The point is that the Martian air is full of CO2. There's not a lot of air, but it's mostly CO2. It's really easy to gather that. You don't have to go anywhere. I said you can be like a tree. You inhale, you exhale. In our case, we inhale oxygen and exhale CO2 because life, when it arose on Earth, poisoned the atmosphere and filled it with this noxious, toxic oxygen stuff. But we rather like that because it's good for burning things. So just go there and inhale it and exhale oxygen for that propellant tank is a very exciting prospect. Ice is exciting also. We just talked, there was a question about that after the last talk. You have to go somewhere, you have to dig it up, you have to process it. It's harder, and you only are going to save, not that 7 tons is unimportant, but it's nowhere near as important as 27. Finally, I've been saying for years and years, as have many other people, Mars is not Earth in many, many respects, and when we've designed for Mars, we have to keep that keenly in mind. Mars is a place where, if this room feels a little chilly now, it's because the air is chilly. If the air is very thin, you don't care so much about what temperature the air is. What you care about is whether the sun is shining on you. So if you are, for example, standing up on the North Pole of Mars when the sun, when it's not wintertime, and someone else, your twin brother, is standing up on the equator of Mars, you'll actually be warmer on the pole because the sun is hitting you full frontal on the pole, and it's hitting the top of your head on the equator. So don't think about things like temperature the same way on Mars as you do on Earth, because we're not walking around in this soupy stuff that we call air. So just, again, a precaution. Think like a Martian in designing these things. So anyway, MOXIE, let's get to it. MOXIE is the Mars Oxygen ISRU experiment. I never liked embedded acronyms, but it's sort of an homage to when this was first done in the 90s for the 2001 mission by a team at Johnson Space Center, and they called it MIP. The Mars, at that time, they called it ISPP experiment. So as an homage, we put an acronym in the middle of the name also, got oxygen. The people, first of all, the work is mostly being done at JPL. I lead the science team, the investigation team from MIT. Jeff Maelstrom is the project manager. The science team is a bunch of people. I won't go through them except to mention Jeff Hoffman, who's the deputy PI. Jeff and I teamed up for the first time since 1975, when I was his graduate student. He went off and joined the astronaut corps and has flown around the world many, many times. And I went off and got involved in the business of sending instruments to Mars. So between the two of us, we teamed up to propose something that brings these two enterprises together, human exploration and robotic exploration in preparation for human exploration. The rest of the people there are a couple of experts in ISRU, a number of people who have expertise in the technology, the electrolysis technology for turning CO2 into oxygen, and a few people who know a lot about dust on Mars, and I'll get to that soon. So here we are. We got this opportunity to fly this human exploration payload on the 2020 Rover, so that's going to land in 2021, launch in 2020. This was where they were putting us when the proposal opportunity came out, over in the front of the rover with all these other instruments with whom we share. These are our shipmates with whom we share resources. Now, since that time, of course, lots of things change. So they actually, you notice, this changed so much that the whole rover is rotated by 180 degrees in the current design. But MOXIE's in the same place, so that shows you how important we are. They turned the whole rover around, left us in the same place. I guess another way to look at that is that we're the ballast that holds it down when they're using the coring tool. We're kind of like the sandbag in the back of your car. Anyway, that's where we're going. This is a nice engineer's vision of how MOXIE works, and what I want to draw attention to across the middle is this box, CO2 acquisition and compression. That's the harvesting part. That's sucking in the CO2. It's important. It's hard. The next box, O2 production, is turning it into oxygen. That's what everyone focuses on, and that's hard too, but I won't say it's harder. It might even be easier. Those are the two important steps. The next one, composition, measurement. Well, yeah, if we just sent MOXIE to Mars and it made oxygen, and we said, yeah, great, we made oxygen, we would not have learned a whole lot. So there's a lot of emphasis put on instrumenting the dickens out of this thing, and so that we can really learn something from it. This is what MOXIE is going to look like. That picture of the rover, you notice we were in the belly of the rover, originally in the spot that was commanded by the SAM instrument you heard about a couple of speakers ago. And so that space is not changing. This is the same rover that is currently up on Mars with new payloads in it. So we were told from the beginning, your volume may not grow. That's quite a challenge. Everything grows when you build a flight instrument. The mass grows, the power grows, the heat grows, the data volume grows, and those things have all grown. Our volume has not. So down in the lower right, when everything's buttoned up and the sides are put on, that's what MOXIE will look like. The yellow box is the part that makes the oxygen. Behind it, the pink box is the part that sucks in the oxygen. So let's start with the part that makes the oxygen. This is, I was going to say kind of a fuel cell. I'd say it is a fuel cell. It's the kind of high temperature fuel cell that uses ceramics to do the electrochemistry, ceramics with a voltage across it. Now, the only difference between this and a fuel cell, we put in carbon dioxide. The carbon dioxide hits this cathode, which is a lot of nickel, a lot of elemental nickel at very high temperature. It's a catalyst. It breaks the CO2 into CO and O. Okay, so it doesn't go to C plus O2. It goes to CO, carbon monoxide, plus O. And then the O, or as you see, the O, minus, is drawn through by the voltage. It's drawn through this ceramic electrolyte. It's a zirconia, scandium doped zirconia electrolyte. And it's the only molecule that can pass through, the only ion that can pass through this stuff. It's selective for oxygen. So what comes out the other side is pure oxygen, and of course recombines quickly to O2 and comes out the other end. So CO2 in, CO plus CO2 out, and oxygen out. We don't burn all the CO2 because we would risk actually depositing carbon if we did that. We use about half of it. And then you stack up a whole bunch of these. So that's how this thing works. When I say it's a fuel cell in reverse, in a fuel cell, you would put in the oxygen, you would put in the CO, which is the fuel, you would burn the two, you would get CO2 out, and you would get electricity out. We do just the opposite. You change the wires. You literally change the polarity of the wires, and we put electricity in, we put CO2 in, and we get the oxygen out. Okay, it looks like this when you stack up lots of them, which is what we do. It looks like this when you build it. The stuff on the outside, the pink sort of clay-like blocks, that's all the laboratory implementation. The stuff between those blocks is essentially what we will fly. Most of what you're looking at are these so-called interconnects, the orange things between the actual cells. You have to put a structure that electrically connects them and has channels for all the gases to flow through. That's what takes up most of the space. Okay, the other part, the sucking part, the collection, the harvesting of CO2 part, this was quite controversial. There's a lot of people that promoted cryogenic approach. You freeze the carbon dioxide down, and then you warm it up, or you absorb it in an absorption bed and do the same thing and pump it out. The problem is whenever we try to do something like that in the design phase, first you have to collect your CO2, and then much later you get to make the oxygen, and we just want to turn on a switch and make oxygen. So in a confined space like this was really we were convinced this was the only technique that works, was just what you would do on Earth, which is you want to compress something, you buy a compressor. So this is a scroll pump or a scroll compressor. Conventional technology for Earth, making it work for Mars, well, that's something else. And we're doing that. Air Squared in Colorado and the Boulder area doing a fabulous job at making all that work. They had a big major review yesterday. Everything went very well. So how does this all work? This is, again, an engineer's drawing of a day in the life. And what you're looking at on the left-hand side there is, we turned it on. We burn about 20 watts just running all the electronics boards and whatnot. And we have to heat this whole SOXE system, this electrolysis system, up to about 800 C. So the first thing you have to do is just heat it up before you even start. That's that 230 watts that's coming up there from the left. So you do that, you You warm it up until it's ready to go. There's a couple of other things you have to warm up at the last minute that kicks it up to 250 watts, some sensors and things. Then you're ready to go. You shut off all those heaters, and you turn on the big power supply to do the electrolysis and run the pump and do everything else, and that's the 320 watts. We do that for up to an hour and a half or 2 hours, at which point we've used up all the power on the Rover. And this is the problem. This darn Rover, it's, the thing's as big as a Mini Cooper, and it runs off of about 100 watts. This projector's burning a lot more power than the Rover's burning. So we store up the batteries. Nobody else runs but MOXIE for the whole day. We run for a couple of hours, we shut down, and it recharges. So as a result, we'll do this every month or so, once a month, because there's other people that want to turn too. So that's how MOXIE works. This is what a full-scale MOXIE system would look like. This is something that Ceramatech actually built for another customer, and it's about the right size you would need on Mars to fill up this propellant tank. Okay, so why is this hard even to do if it's already been done? Well, first of all, on Earth, people always use water to help things along. We've learned, Ceramatech mostly, has learned how to do this very effectively only using dry CO2. It's an art more than it is a science. Normally when you do this sort of thing, whether it's a fuel cell or it's inverse here, an electrolysis system, you turn it on, you heat it up to 800 C, you never turn it off unless it breaks. This time, every time we run, we're heating it up and cooling it down. That's pretty rough on all the components of a system. So we've had to learn how to do this reliably without it degrading. Two things, oxidation and coking. Okay, these are the opposite situations. You can oxidize your nickel at the cathode, or you can go too far in reacting the CO2 and start depositing carbon. That's called coking. Most of you are aware that MOXIE is also a soft drink. I've heard tell that Coke is also a soft drink. Somebody told me that. So coking is kind of interesting that MOXIE and Coke are fighting it out on this instrument, because they also fought it out back during the Depression, and Coke won. MOXIE's going to win this time. Anyway, those are the two. We have to balance between those two. You go too far in one direction, you get Coke. You go too far the other direction, you get oxidation. We're operating at low pressure, which means everything has to be sealed and compressed, all these layers, so the gas doesn't just force its way out. You don't have to do this on Earth. And not only that, now we have to compress it, we also have to thermally insulate it, and we also have to survive shock and vibe. And so we're asking insulation to, we're doing what you shouldn't do with insulation. We're saying we want to squeeze on it and not have it change dimension. And we want it to tolerate being vibrated and not have anything move around inside. And we still want the insulation to work to keep the heat inside. And that turns out to be maybe one of the toughest problems in the whole project. But you don't want it, you can't put the springs inside the 800 degrees C hot zone. So all these things have to work together. So those are the kinds, just to give you an idea of what we're learning from doing this. We're learning how to do these kind of devil-in-the-detail things that make it hard. Okay, so I want to talk a little bit about what limits how much oxygen we can make. That's the first question people always talk about. The SOXE itself can make up to about 20 grams per hour. And that's about as much as one of you sitting, if you were sitting here for an hour, which you have been, that's probably about how much oxygen you've been consuming. Of course, that's not why we're doing it. We're doing it to fill propellant tanks, but it's a good metric. However, you got to supply power to do this. This rover is power limited. We're in a closed space, so if we burn too much power, we'll get too warm. Mars is cold, but it's easy to get an instrument too warm. So that limits our production to about 12 grams an hour. Turns out you've got to suck in a lot of air. We're very limited in volume. We can't make our pump real big. So if we land at a high elevation, there's about a factor of 2 difference in the pressure and the density of air from low elevation to high elevation. And right now, all the scientists on the mission want to land at high elevation, because on Mars, in complete contrast to Earth, higher elevation stuff is older. On Earth, lower elevation stuff is often older, and the high elevation stuff hasn't eroded yet. But anyway, the scientists want to go to the high stuff. So we won't have as much air to suck in as we wanted. And again, the pump can only do so much. So for most of the landing sites, the pump's limiting us to about 10 gram per hour. Just can't suck in enough air. And then we have operating margins. We don't know, can we use 50% of the CO2 without making, coke? 70%, we're still learning. The season and time of day, it turns out, I'll show you in a moment here, the pressure on Mars goes up and down by about 30% because of all that CO2 that Adrian Brown was just showing you deposits on the polar cap every winter, northern winter and southern winter, that actually is coming right out of the atmosphere, and the pressure goes down, and if the pressure goes down, MOXIE has less air to suck in. So what does all this mean? It basically means if we're looking at how much oxygen we can produce on the y-axis here, we're looking at the atmospheric pressure. Let's say 50% utilization. That means we use half the CO2 with our existing pump. So depending on where we land, in the fall when the pressure is low, we can make 8 grams an hour. In the summer night when the when the pressure's high, when the pressure's low in the summer night, we can make less. When there's a dust storm, the pressure actually goes up, we can make a little more. So and if we landed at a Viking site, we'd be Fat City because the pressure would be 7-8 torr, not the sort of 5-6 torr we're expecting. So let me put all this together for you. If you know Ohm's law, V equals IR, voltage equals current times resistance. The current is the oxygen ions being produced. Literally, when you measure the current, you measure the oxygen. The voltage is the voltage you apply. 1.20 is safe. We can probably go up to 1.46, which is called thermal neutral. And to complete Ohm's law, you need a resistance. That's what ASR is. It's the area-specific resistance. So that's going to determine how much oxygen we can make. Now, current limit says we can't make more than 12 grams an hour. That's why those curves flatten out. The ASRs we're measuring, I put down 2.3. Latest results were 1.6. It's getting better all the time. So at 2.3, you can see at 1.2 volts, we're up at the current limit. We're making 12 grams an hour. At 1.6, we have to lower the voltage even more. It turns out this is how much oxygen, carbon dioxide we have to work with on a fall day. Depending where we land, we'll be somewhere from that top of that box to the bottom of the box. On a summer night, depending where we land, somewhere between the top of this box and the bottom. So as I said, 9 to 11 on a fall day, 7 to 9 on a summer night, and that's what MOXIE expects to do on Mars. Okay, but it's important to go through that because this is what we need to know to build a system to work when we're sending humans. What's limiting it? How big do we have to make the pumps, et cetera? I think Adrian also gave a shout out to my work on Phoenix. Thank you. This is the only thing I'm going to show from Phoenix, which was the highest resolution microscope picture that has been and probably will be taken of Martian dirt. Martian dirt is really interesting at this scale. This whole thing's about 2 millimeters. And except the little atomic force microscopes, about 10 microns. Draw attention to all the kind of just weird random shape, ubiquitous red stuff around the edges. That's the dust in the air. That's the stuff we're going to be dealing with. Mars is not, as Bob Zubrin said, it's not like the Martian. You're not getting huge storms, but it's kind of like a smoggy day in LA. Things will get dusty. And the trouble is, there's not a lot of air on Mars, so a little bit of dust and a filter really will be game over. Imagine if you ever breathe, say, through a dust mask, right? You have to suck in a little bit harder, all right? But you can do that because you have one atmosphere. A little bit of dust and a filter will kill the experiment. It will kill the instrument. So this is one of the things we've also been worried about. I'm going to show one more metric and sum up, which is here's where we are in terms of our power usage. You would like to put all of your power into actually making oxygen. That's the SOXE part. That's 60 watts out of this 320. The electronics part, fortunately, won't grow very much as we make a larger scale system. MOXIE's 100 to 1. That's okay. Sensors won't grow. The heaters won't grow very fast because as it gets bigger, we won't be losing as much heat. We have one big insulation around it. So that's okay. Right now, the pump is 110 and the SOXE is 60. We have to work on that ratio as we get bigger and bigger to try to get more of the power into the electrolysis. So what have we learned so far? That's why we're doing this, to learn stuff. You know, that's why you do a tech demo. So one thing we're learning is that we can make that electrolysis system work. It's, you know, if there's a recipe, it's like a recipe in a cookbook. You still need the cook to make it come out right. The pumping takes more than half the resources, as I mentioned. The whole insulation, sending something to Mars, compressing, insulating, and shaking, that's hard. A little dust makes a big difference in a thin atmosphere. The devil's in the details. You know, don't focus on doing electrolysis, focus on the system engineering. And it's nice to have Matt Damon as your spokesman for your technology. So there we go. MOXIE is brought to you by all these people. These are all the co-investigator institutions. I mentioned the three wings of the three pillars of NASA holding us up, and the various co-investigator institutions. Special attention to Ceramatech and Air Squared, who are respectively making the SOXE and making the scroll pump for the project. And also special thanks to the amazing JPL project team. This is the MOXIE test bed. All we have to do to be ready to fly is to take all this stuff and put it in a box this big, and we're good to go. So thank you, JPL, and thank you to everybody, and thanks to all of you. If there's any time, I'll take a question.
Hi, Bob Terry, Mars Society. Two questions. Would it be possible to build a larger scale object and then test it in Martian conditions in the Plumbrook vacuum chamber, and you wouldn't have to face all these problems of compartmentalization? And if you go to Mars, can your astronauts actually construct a larger housing with more efficiency? And how do you compare the power needs of condensation of cryogenic collection versus the power needs of that pump? Because it seems like a pig.
Well, there were a whole bunch of questions in there. Let me try to go through them really quickly. First of all, yes, building a full-scale model on Earth, this is really the time to do that. Now, of course, building these things costs money, and you know, there's a lot of negotiation that has to go on. But there is some effort, some investment in ISRU to build a full-scale system. Whether it's MOXIE-based or one of the other techniques you mentioned is not yet clear. The power comparison between the different techniques for collecting oxygen, cryogenic, et cetera, I think that's a system problem. And for a quick example, if you also have to do cryogenics to liquefy and store the oxygen. So if you've already got a big cryogenic system there anyway, that weighs in favor of doing cryogenics to collect. So it's not just isolated, you know, how they compare. And was there a third part to the question? I've forgotten. Oh, yeah, the relative energies. The pump, thermodynamically, you know, is going to win. Whether it wins in practice because of friction and all the other pragmatics, you know, the devil in the details, not clear yet. Okay, you might hear more about that later. I think Tony Muscatello is going to talk.
Okay, I got the mic, so I get the next question.
Go for it.
Will this technology, assuming it works, scale up? Because by my back-of-the-envelope calculations, this thing will produce maybe a kilogram of oxygen a week, and you know, to make 20 tons of oxygen for a return mission, you know, how long is that going to take? 200 years?
Yeah, well, no, that's right. What we need to do for Mars, for the Mars human mission, the first one, is make about 2 kilograms an hour, not 20 grams an hour, and so 100 to 1, 200 to 1 kind of scaling. So what that means in practice is you'd be looking at something about 1 meter on a side. The SOXE scales up. I already showed you a picture of a unit that's been built for another application. That's the right size. You just take lots of these little stacks and stack them up. 100, 200. The pumps scale up well. I mean, in fact, the funny thing about the pump, we go to a little company like Air Squared because they're the only ones that make little scroll pumps. It's much easier to buy a big one, so they'll scale well. It turns out one of the toughest things we're going to have to scale is actually the filtering. the problem I mentioned quickly, with the dust, we're going to have probably one whole face of that thing, if we use conventional HEPA filters, will be a thick pleated HEPA filter to get through the 1 or 2 year lifetime we need without clogging up. There are other approaches other than filtering. So that's a problem that still has to be solved. Yes, it will scale very well. And by the way, I'm happy to stay around. I know after we dismiss for lunch, I'll stay up here if people have additional questions.
Thank you. I was going to ask, is there any way to utilize the waste heat? And if not, how long does it take to cool down? And is that a problem for the Rover?
I'm sorry, utilize the waste heat from MOXIE?
Yeah.
Not really utilize the waste heat, no. There are ways, for example, to utilize the waste CO2. There already is some recirculation of the waste heat in that you have to heat up the gas going in, cool it off when it comes out, and you can use that heat from cooling the gas to heat up the new gas coming in. But what's waste heat is, it goes a lot of different directions. It sneaks out along the wires. Some of it just conducts out and radiates. So not really. But remember, as it gets big, heat comes from a surface, and the surface to volume ratio works in your favor as you scale it up. So that will become a much less important factor when you build something that's a meter cube. And I think that's the last question, but as I said, I'll stay here and happily answer more.